Conductors. Let's think back to conductors, neutral conductors, like a Swiss conductor, in a uniform field. A neutral conductor in a uniform field. Let's think about what would happen, because remember what was special about conductors is that charges are allowed to move. Okay? So let's start just with our uniform field. I'll draw it, this time it's better to draw it in terms of field lines rather than vectors. So I'll draw field lines for this one like that. Okay? And we're going to apply a uniform field, E, let's call it EAPP as a subscript for E applied. Is the field we've created in space. And let's drop in a uniform, let's drop in a neutral conductor. Let's see, draw it kind of like that. A nice little cylinder that looks kind of like that. And I'll get that off there. Like that, okay? Now, we know what's going to happen is that this electric field we applied, it's going to exist inside the cylinder. There's no reason it wouldn't. You have superposition. All these electrons and protons are running around making their own fields, but sure enough, that electric field, why wouldn't it be there? And when it's there, we know that in a conductor, the charges are free to move. In a metal, if we assume this is a metal, it's the electrons that are free to move. So this little electron is sitting there minding its own business. We turn on E applied, and it's going to move. And which way is it going to move? It's going to move this way. Okay? And it's going to end up over here, a little negative charge over there, because it's going to feel a force pushing it that way. It's going to stop there because it can't get out of the metal. Right? So they're free to move within the metal. They can't leave the metal. Now actually, the thing was neutral. We moved a charge here. We have to have actually left a positive charge there. Sometimes in physics we call it a hole. There's a hole in the electron C, so we call a hole a positive particle. I guess if it started here, it left a hole here, but if there's a hole here, this electron would jump in and fill it and leave a hole here, and this electron would jump in and fill it and leave a hole here, and it would make its way down. Anyway, in the end, we draw it kind of like that. Positive particle on that end. Okay? So let's think about what's happening to the field inside the metal. So like I said, you start out with E applied. Okay? This field is being created by, say, a giant charged plane here. It exists everywhere. But this little separation, this positive and negative charge, create a field we'll call E induced, and it's probably little, because it's just one little atom and one little electron and one little lack of electron. It doesn't make a very big field. So the net field inside the material is still that way. If you vectorially sum these two, still that way. So what happens? Another free electron says, hey, there's a big field there. I feel a force. And it comes over here. Negative. Puts a positive hole there, makes E induced a little bit bigger. Okay? But still, the net field's that way. So another electron says, okay, I'm going over here, and which leaves another hole over there, and E induced gets a little bit bigger, like that. But there's still a field that way. And yeah, I'm going to do it again. Another electron comes over here, negative, leaves a hole over here, positive, E induced gets a little bit bigger, like that. So as you can see, you build up negative charge here, you leave positive charge there in this conductor, and it'll keep happening. And E induced will continue to grow until something special will happen here. What has happened here is that now the induced field inside the metal equals the applied field inside the metal. Okay? So, and then the field is zero. So once you make the field zero in the metal, things stop moving. Okay? So what's going to happen is charges move until I'll say until E induced, the thing you're making, equals minus E applied. Because when that happens, E total is zero. And then they stop moving. Right? This is a condition that we call electrostatic equilibrium. Or I'm just going to write it EQ, because I get tired of writing electrostatic equilibrium over and over on the board. It's similar to the mechanical equilibria you learned about, right? When all the forces are zero and everything is still, that was mechanical equilibrium. Here, it's electrostatic equilibrium. The electric field is zero and all the charges are still. Same idea. Okay? So when you're at electrostatic equilibrium, the charges don't move. Because the force on them is 0, and therefore E is 0 inside a conductor. So if we had this conductor just sitting here, popped on the applied field, the charges would immediately do this. It happens very fast. Immediately do this, create an induced field, and E is 0 inside the conductor. Okay, so that's the main thing to take away. The electric field inside a conductor will always be 0 if you let it get to electrostatic equilibrium. Let's look then at something slightly different. That was a neutral conductor. What if we have a charged conductor? Is that different? And basically, the answer is no. Let's imagine a charged conductor here. So a sphere of a conductor, and let's drop some charge on it, some positive charges. Here we go. Here they are, floating around inside this charged conductor. Well, they're going to experience a force because, due to each of the other charges. Right, the conductor is neutral, so on average, the conductor's charges don't do anything. But this feels this force due to this. It wants to go that way. This charge feels the force due to all these. Repulsive force wants to go that way. This one feels those. Those two kind of cancel. Those kind of cancel, but it feels a big one there. Goes that way. So what happens is, in a charged conductor, the charges go to the surface. Okay. So this is a charged, right? You could also do that trick where we induced a charge separation. What if this charged conductor were sitting here, and we had a neutral conductor here? Well, what would happen? Well, this thing is net positive. It would suck negative electrons there. Right? It would suck negative charges this side. It would leave positive charges on that side. But again, the charges always go to the surface. They move to make the field 0, and often they end up at the surface where they can't get out anymore. They can't leave the metal. That's as far as they can go. So in a charged conductor, you have a fairly similar situation. The charges move until E in the metal equals 0. Right? They reside on the surface, and the charges reside on the surface, even if it's excess charges. And this all assumes that we've reached an electrostatic equilibrium. Okay? So my point really is just that a neutral conductor or a charged conductor, it doesn't make a difference. It's always the case that in a conductor at equilibrium, you'll always have the field inside be 0. And the reason is, if the field weren't 0, the charges would move. Where would they move? Well, they would move until when? Until the field is 0. Right? The field has to be 0 in the metal, because that's the only way the charges can stop moving. So we're going to keep working with that idea, but definitely keep that in your head, is that the field inside the metal has to be 0. So we've thought about the electric field inside a conductor. It's always 0. Now let's look at the electric field outside of a conductor. All right, so let's draw just some surface of a conductor, some lumpy thing. The details of the surface don't matter right now. And although we usually use metals for conductors, let's imagine the free charges here are positive, just to make the drawings nicer. And let's have it be charged. Okay, so say this conductor has some charge on it. We know that the charge will move until the E field inside is 0. That's what we covered before. Because it'll move to make the field 0, because if the field weren't 0, it would keep going. Right? So the charges will move until the field is 0. So they'll collect somehow on the surface of this conductor. And they'll arrange themselves in a way to make the inside 0. Maybe it's because the conductor is charged. Maybe it's because it's been put inside an electric field. Doesn't matter. The point is, they will arrange themselves in an electrostatic equilibrium. E field inside will be 0. So let's think about now the E field outside. So anywhere you go, the E field just outside could exist, and in a Cartesian coordinate system it could have 3 components, x, y, and z. Let's do this in 2D since we're writing on the board and say, well, it could be in any direction. And in that direction you could build it up into an E field that is perpendicular to the surface and an E field that is parallel to the surface. Could happen. So I don't mean inside. Inside it's 0. What is the field just outside? That's the question, right at the interface. So this is possible. Any field that exists right outside could be broken into those 2 components. So we just have to think about which of those components can exist. Okay? So the E field just outside actually can exist in this direction, perpendicular. Because you would say, well, whenever there's an E field, inside it goes away because the charges can move in a way that will cancel it. Well, this is the one way they can't move. They can't move out of the material. They're stuck in the material. So E perpendicular does not equal 0 because the charges can't move outside the conductor. Because to move outside the conductor, they have to move perpendicular to the surface. Now, let's think, can there be a lateral field? Well, in this case, there can't. If there were a field vector that built up that way due to this charge, what would happen? Well, this positive would be pushed that way a little bit. It would leave it a little bit negative there. It would make a field that would cancel that field. And if it wasn't enough to cancel it, it would do it a little bit more. It would do it until this field is driven to 0. 3 charges, and then that's enough to kill it. Okay? So for a field that's parallel going along the surface, E parallel, it does equal 0. Because in that direction, along the surface, the charge can move. So it's the same argument, the same idea for why the field is 0 inside. Also occurs for the field just outside. It's just what you'll end up with is only the perpendicular field can exist. So if you look at the field of this charged conductor, in this case, the field lines will all be perpendicular. Here it's kind of going off that way. Here it'd go off that way. So it's easy to draw the field around a charged conductor. You just draw the lines perpendicular to the surface everywhere. Or even if it weren't charged. Even if you had some negative charge out here, and these field lines were just between the metal and the negative charge, they would still also, they always terminate perpendicular to the surface of a metal. Okay? So E field is always perpendicular to a metal surface. So we know the E field right outside of a conductor has to be perpendicular. Let's see if we can figure out what the magnitude is. So this is E just outside a charged conductor. Okay, so let's imagine we have some slightly curved conductor. Ultimately, since we're just calculating E right at the surface, it doesn't have to actually be perfectly flat. Right? We did the infinite plane. We calculated E for all distances from the surface. Here, we're really just calculating the E right at the surface. And when you're right at the surface, everything looks like an infinite plane. This curvy stuff is really far away. Okay? So let's not worry too much about it being an infinite plane, but let's still make all of our symmetry arguments. So our Gaussian surface, in this case, needs to take advantage of the fact that this charge, sigma, on this big curved surface is going to create an E field that always sticks up. Right? In the metal, it's going to not create any E field. Okay, but here it's always going to point up. So that's the case where we want something with a flat surface with an A vector pointing up. So that's this Gaussian cylinder. Or we could do the pillbox, but the cylinder is easier to draw. Okay? So there is the area that's actually inside the cylinder. Okay? The cylinder has a top and a bottom area of A, and the area in the metal surface is A. So let's do Gauss's law. The integral of E dot dA around the curve is the charge enclosed over epsilon naught. And here we break it up into 3 parts again. The integral of the top of E dot dA plus the integral of the sides of E dot dA plus the integral of the bottom of E dot dA equals the enclosed charge over epsilon naught. Okay, well, there's going to be some field sticking out the top. The A vector goes up. We know, since we're treating this essentially as a plane, infinite plane, the E field sticks up. So, as we've argued many times, this is EA. The sides, we know, because the electrons would move, right? If there was a field this way, the electrons would move. So we know that there's no flux through the sides, is that if A vector is that way and E is that way, they're perpendicular to each other. So that's 0. And at the bottom, it's 0, because the E field inside a metal in equilibrium is always 0. The charge enclosed is just sigma times the area, sigma A over epsilon naught. So in the end, you get that the E field of a charged metal does not depend on the area of your Gaussian cylinder. It's just that E equals sigma over epsilon naught for a charged metal. And we kind of got away with ditching the plane, or the infinite aspect of the plane. And it was sort of a trick, and I'll make sure you see it. In the infinite plane, we calculated the E field in all of space. Okay? Here, we just want to know it right at the surface, and it's being forced to be perpendicular. We don't really rely on symmetry to make it perpendicular. It's actually the fact that we know the charges can move along the surface that always makes it perpendicular. So really, we could zoom in to where the Gaussian surface is a teeny little thing. And that actually takes care of most of our symmetry arguments that we need. So that's why I kind of drew this as a curved surface. It doesn't rely on it being an infinitely flat surface. It can be curved. And I see a question there, and I know what that question is. I know for sure. It's where is the 2? Because that comes up every time. You get a formula for the metal that's different from the formula. Uh-oh, computer breakdown. Whoa, okay, whoa. Luddite is quite unhappy, so he's writing in really big font. Luddite, which is an interesting name for someone taking a MOOC, says that the charged metal field, right, is different from the charged plane. Why do we get sigma over 2 epsilon naught for a charged plane and sigma over epsilon naught for a metal? And the reason is those are not the same thing. Okay? It is true that for both you have a surface that is a charge sigma. Okay? And when it's just literally a sheet of charge, there's no material involved. It's just a sheet of charge. It creates an E field both ways. But when it's a metal, when it's sitting on a metal or a conductor, it only creates an E field this way. Okay? So charge has a certain amount of oomph to create an E field. Right? It can only create so much. There's so much flux it can create. It creates a finite amount. So the same amount of charge is going to create a certain amount of E field. If it has to create it in both sides, it makes half as much. E is sigma over 2 epsilon naught. But if it only has to create it on one side, if it throws all of its charge-making excitement into one side, then it's just over epsilon naught. So it's physically 2 different situations. That's really the reason. They are not the same. Even though they are both a plane of charge, one is in free space, one is sitting over metal. That's the reason. So we've talked a lot about how to make a field. Let's talk for a minute about how to get rid of a field. Let's look at electrostatic shielding. Okay, so let's think. How would you do it? What would you build if you had to do this? So sort of 2 things come to mind that we've been thinking about. One would be a shell. Let's make an enclosed room, and let's make a shell just of charge. Okay, so let's make a shell of charge. Right, so this is really a 3-dimensional shell, and there are charges throughout this region, and they have some charge density rho in this volume of this shell. And the question is, will that keep an electric field out? You could also think about a metallic shell. All right, so I'll kind of hatch mark that to show that it is a conducting shell. It's probably a metal. It doesn't have to be. Okay. So will either of these stop an electric field? So let's imagine then that we have some big whopping charge here plus Q. What will the field be inside? Well, E, the electric field will be 0 due to the shell. And that's a Gauss's law problem that you'll probably do in the homework. You can show that the E field inside this thing is 0. All these charges make fields that cancel out. However, the field due to this will happily go in because it's superposition. E inside here will not be 0 due to superposition. Okay, so this is the real answer. It will not be 0. The shell contributes 0. The shell by itself makes 0, but the field lines out here will just go straight through. I mean, they'll bend around because of the presence of the charge, but eventually you will get field lines in here due to big Q, due to this big charge. So a shellar charge does not screen anything, does not shield you from anything. Let's think about how a metal or a conducting shell might be different. Okay? When the conducting shell is neutral, or even if it's charged, E equals 0, again, due to the shell. A shell itself makes no charge, makes no field. The question is, does it shield from an external charge? And now this will, and the reason is it's different. Okay? This is a conductor, which means the charges can move. So even if it's a neutral conductor, the charges, both the positive and negative, can essentially move. So if it's a metal, the electrons are free to come over here and build up and essentially cancel out big Q, or to attract to big Q, and then you have a big Q, positive Q, and essentially a negative Q there. So you'll have a bunch of charge here, and that'll leave some positive charge over here. So what it'll do is it'll warp the field lines. Instead of having them sort of bend around and go through, every field line that approaches the metal surface, we know, outside of a metal, will end perpendicular to the surface. And that basically means the field line is terminating, right? Field lines always start on a charge, and they always terminate on a charge. So this metal shell is going to throw up a charge distribution to terminate all of the field lines right on its surface, just like this. That one will come out and probably go right there. One might come out and do like this. And it does that due to the properties we talked about of a conducting object. Basically, these electrons will move until they can't move anymore. They'll move until all these fields are perpendicular to their surface. And once that field line hits perpendicular, it's finished. Therefore, no field lines get in. So it is actually true that inside a metal shell, E really is 0 if it's empty. So now we're going to demonstrate the shielding we've just been talking about. So I have Catherine here with me.
Hi.
And it's a complicated demo. It takes 2 people. And has a lot of equipment involved. So let's remind you what everything is. First, there's my favorite, my Teflon rod. It's got the Teflon tape on it, and I'm charging up the Teflon tape. So the Teflon tape is nice and negative. It's got a Van de Graaff generator. So this is basically something that gets really charged up. This belt runs back and forth, picks up charge in the base, dumps it in the metal can, and it gets a very high charge. Will throw big sparks. You've probably maybe seen people play with these before. The third thing is this, and it's named after the greatest scientist that's ever lived. Catherine, who do you think is the greatest scientist that's ever lived?
Probably Einstein?
No. Most common answer, Einstein. Einstein was a theorist. You have to be at least half theorist, half experimentalist to be the greatest scientist that's ever lived. Guess again.
Faraday?
Yes. Very good. Faraday. Maybe she's heard of a Faraday cage. So Faraday was the greatest scientist that's ever lived. I don't have time to explain it right now. I'll recommend you a book later. But there is no question he was. So this cage is one of the many things named after Faraday, and it's basically a continuous metal cage. And as we just learned, if you have a metal shell, it shields electric fields from getting inside. So what we're going to show you, so Catherine's going to take the rod and the tape. I'm going to turn the Faraday cage on. And now we have a very large charge building up, and you can see it's even arcing. But the main thing to see is that the negatively charged tape doesn't want to go anywhere near the Faraday or the Van de Graaff generator. There's a large electrostatic repulsion between the two. And now Catherine is going to take it and hold it near the Van de Graaff generator, but inside the Faraday cage. And when she does that, you're not going to see any electrostatic repulsion. See? The tape just hangs there. The tape is still charged. The Van de Graaff generator is still charged, very high, but there's no repulsion because the cage is shielding the electrostatic field. Okay? Now, that's the normal way to show you that a Faraday cage works, but I want to show you how much I really believe in a Faraday cage. It's like a religious thing with me. Anything named Faraday, I have a high degree of faith in. So what we're going to do is I've got those sparks going again, and I'm going to get in the Faraday cage up here, and I'm going to put my tongue here where it's starting to spark, but it won't get me because I'm protected by the Faraday cage. Here we go. So I'm going to put my tongue here. See? Don't feel a thing. Put my nose, eyeball, nothing. And the reason is the Faraday cage makes all the field lines that are coming off this thing stop. They stop right on the metal surface and they can't get through. That's why I never felt anything. No electric field, no particles got past the Faraday cage. The one thing you may ask is this thing has holes in it, right? It's not a solid metal shield. It's actually just this sort of mesh, and one reason is so you can see through it. And it still works. Nothing gets past the holes because as long as all the objects we're dealing with, this big sphere, my tongue, all these things, as long as they're big compared to the size of these holes, in terms of electrostatics, it's essentially a continuous metal film. So don't worry about the holes. They will affect other things, but for this example, it doesn't matter. It's essentially a continuous metal cage. So there you have it. Faraday cage, great name, always works.